So now for the 2 remaining hours today, we will talk a little bit about wall-bounded turbulence, or turbulence in general, and this part of the school should really serve as a sort of introduction to all the lectures that will come after. So it's intentionally going to be fairly basic, so we will go through all the major concepts of turbulence, and in particular wall-bounded turbulence. So if you feel that you've known or that you already know everything here, that might be very well true. Please just bear with me. I hope, in particular, in the end, I will have some interesting results, in particular visualizations of flows, visualizations of wall-bounded flows, such that you really get a feeling of how a turbulent flow at reasonably high Reynolds number actually looks like. So, the topics that I would like to talk about are these 4 things here. So we'll start, as Henrik did, with an overview and also a summary, a little bit about the history of researching wall-bounded turbulence. We will go through governing equations, essentially once more, after Henrik has already done that to some extent. We will then go through the basics of the turbulent wall-bounded flows. We will look a little bit on the scalings close to the wall, and we will also look a little bit on budgets of kinetic energy in a region close to the wall. And in the third part, I'd like to show you a little bit what kind of flow structures really are present in turbulent flows close to the walls. Of course, one of the key concepts there is to have streaks, now not the laminar streaks that we have seen in bypass transition, but rather the turbulent streaks. We will talk a little bit about the interactions of various scales in boundary layers, and then, as I promised, some visualizations. And then, don't be afraid here, the last point, the homework problem. It's a nice little problem that when you can think about it. So let's start with an overview. So turbulence. So it's really very, very basic how I like to start. So the major, or where people have most experienced turbulence is, of course, in such a situation when you're in the airplane and suddenly the captain says that you have to fasten your seatbelt because there is some turbulence around you. Of course, there is always turbulence around you, not just when you have to fasten your seatbelts. Another aspect of turbulence is, of course, when it comes to geophysical flows, storms, for example, or maybe more everyday experience. If you try to stir your coffee cup, you also exploit the enhanced mixing caused by turbulence. There is also a movie which is called Turbulence. Can you survive the ride? Does it say there? I haven't seen it. I don't know. Maybe it's good.
There is even a sequel.
Huh?
There is even a sequel to that.
Okay. Well, anyway, so what we usually associate with turbulence is that motion is very chaotic, it's unpredictable. Usually we think it's bad when we just look at the movie. It's probably really what it is. And usually we try to avoid turbulence. But what I want to show now is that although it is all chaotic and unpredictable, there are some things that we can predict about. Let me just add here a few of the key concepts of turbulence, which are very important to always keep in mind. So turbulence is considered to be always time-dependent, so there is no steady turbulence. It's always supposed to be three-dimensional, so it involves all directions. We can make predictions about statistical quantities, but not necessarily about instantaneous quantities. So we always have to refer to statistical concepts. And last, sort of always statement here, it's always dissipative. So it is relying on dissipative scales, which then in the end will lead to these cascading processes. Now, another one of these nice pictures slide, turbulence is all around us, of course. So we have here geophysical turbulence here with this large storm. We also have it here for a volcano eruption in the wake of this airplane, internal combustion engines, around cars, or here also air acoustics around a turbulent jet. So turbulence is all around us. In fact, most of the fluid around us is turbulent. The good thing is that we essentially know what equations are governing turbulence, or any fluid flow. Here I just wrote down the incompressible Navier-Stokes equations, although most of these actually phenomena in the pictures are usually dominated by compressible equations, but these are incompressible. So one of the most important concepts in turbulence is that we know the equations, we just need to find a way to solve them. So the problem is not to find the correct equations, but rather a good way to solve it, either experimentally, so that nature is solving it for us, or numerically when we try to So the problem is really not to find the equations, but find the solutions. So when you see here this equation has here viscosity in it as a major parameter when you normalize it, or when you write it in non-dimensional form, this implies Reynolds number. And this is also one of the key influences of flow. This we've heard before by Henrik. Of course, the Reynolds number occurs here as length scale times velocity squared over viscosity, and it goes back to these experiments before plus 1 Reynolds. And essentially, what here the background is, Reynolds number essentially says whether the flow is laminar, transitional, or turbulent. Another important influence which we will not talk about today, but I think it's on Thursday when the topic will be compressible flows, is the Mach number. This essentially characterizes the influence of the compressibility. The influence of the viscosity usually is confined to a region very close to the surface, and this gives, of course, rise to the boundary layer concept, which is smooth. And this concept essentially goes back to section. Then, of course, we can consider many more effects: heat transfer, fluid structure interaction, acoustics, and mass shift. All of them are not of interest right now in this introduction. So, what do we want in the end when we consider turbulent boundary layers? Essentially, we can consider our goal to be to predict the flow around such a body or an airplane. That means we will have turbulent flow probably here on the wings, on the fuselage. This turbulent flow will lead to enhanced friction, it will cause drag, and in the end, of course, it will lead to consumption. And maybe, eventually, a good understanding of how this turbulent flow is looking like, and what kind of ways we have to influence that, we might be able to reduce this friction and maybe even to reduce the fuel consumption. But of course, this is also not part of today's talk. It's rather sort of serves as an application. Now the question is, let's consider this airplane. What can we really, or how does this flow look like? So let's just put here a little rectangle, this red box here. It's, let's say it's about 20 times 1 centimeter for normal in-flight conditions. And if we zoom in, this is how the flow in such a little 20 times 1 centimeter area on a wing would look like. And then we can again start to zoom in. And then just take the last part here, which is then probably 1 centimeter times 2 centimeters or so for real conditions under flight, and we can zoom in once more. So this is the flow structures that appear on the wing of an airplane. Now you can see if we want to really resolve all that, is it numerically or with an experiment, of course, completely, it's a hopeless task if we really do that. But still, if we want to understand to a large degree turbulence, we actually need to understand the interaction of these really fine scales to these larger scales that are indicated here by this blue circle. This will then give us the understanding of yes, so when we, of course, when we now look a little bit on the literature, of course there have been many books about turbulence. I just list here a few of the ones that have had, in my opinion, the greatest impact. It starts here with Bachelor in 1953 with this little book about ingenious turbulence, and continues through the 70s from Heinze, Longley, up to the very nice book by Pittacus and Longley, which I actually have here, which is called First Course in Turbulence. And although it's a book from the 70s, it's a really nice book to read as a first course in turbulence. So you can have a look afterwards. Then it continues here with Schlichting about the boundary layers. We have here a book by Monsieur from France. Then the very nice book by William Frisch about, essentially it's non-boundary turbulence. It's also it's a very nice book about essentially statistical theory of turbulence. Then the last book here, which probably you all know, is the textbook by Stephen Pope about turbulent flows, also treating everything from free flows to non-boundary flow, about modeling, PDM. This is really has become a standard book in turbulence. So please have a look in these books afterwards. And, okay. Now, so what were really, from a historical point of view, what were the major breakthroughs or landmarks in turbulence? Of course, at first it starts with the boundary equations. I always like to put Euler there as the first one. Of course, it continues with Navier and Stokes, essentially writing down the Navier-Stokes equations as we write them, essentially. Navier. Cousinès came up with a viscosity assumption, and then we have the two papers by Osborne, Reynolds, as Henrik has mentioned. The first one here about the high flow experiments, where you could identify the Reynolds number to be the important non-dimensional number. Then a few years later, Osborne Reynolds came up with the Reynolds decomposition and the Reynolds averaging concept, which is extremely important in turbulence. Then we have Prunty appearing here twice. The concept of boundary layers in general, and also the mixing length theory, which can be considered as a turbulence model. Pi flow experiments were also performed in the 20s, 30s for rough and not rough types. This is also something that we talk about more during this school. Of course, a very important landmark was Carbon, and came up with one way to derive logarithmic velocity profile in the near wall region. Kolmogorov maybe less focused on wall turbulence, but still sort of having a profound impact in understanding or describing turbulence with the scaling of spectrum. And then we have here three landmarks, I would say, from later times in the 60s, the first flow visualizations, where we could really see coherent structures in the flow, particularly the streaks that I mentioned before. 87, so roughly, this is now 20 years ago, more than 20 years, the first direct numerical simulation of a flow that was reasonably turbulent before by Kim Moser. And then just 1 year later, the first DNS of a turbulent boundary layer, performed by Philippe Spallard. It's interesting that this simulation, up to maybe 2-3 years ago, was still the boundary layer simulation with the highest Reynolds number. And it has been used many, many times as reference to compare turbulence models, to compare variables, to compare other simulations. So it was only recently that actually people have reached higher Reynolds numbers. Osborne Reynolds was appearing twice in this list. So of course, he is an important person in both transition and turbulence. I don't want to say too much about it, but I just want to mention these two papers written about Reynolds, not by Reynolds. One is the history on the Reynolds number, essentially what we have here on the board, also how it was introduced as the universe, and so on. This is an annual review of 1990. It's very interesting to read. And also here, another annual review paper, 2006, which appeared about the difficulties or the struggle Reynolds had in actually publishing his landmark papers. So you see their referee reports back and forth. It's kind of interesting to read how his peer review system is working. So now let's go a little bit more into the details of equations. This is essentially the same slide as Henrik was showing, just the basic governing equations for incompressible flow. So we have the continuity equation, which is the conservation of mass. And we have here the momentum equations, which goes to the conservation of momentum. Then what one does is one introduces reference scales. We have the velocity scale and the length scale. With that, we define the Reynolds number, and then we can non-dimensionalize governing equations, essentially leading to this system of equations. Now, it's important to realize that these equations at this stage do not have anything specifically to do with turbulence. These equations are valid for laminar, for transitional, and for turbulent. There's no difference. Essentially, the only job we have to do is to somewhat solve these, or somehow solve these equations and then interpret the results. Maybe just as this is sort of an introduction lecture to turbulence, I just have this one slide about the summation convention, something that people usually use in turbulence. It's a way to write sums like this, which usually appear when writing terms for which are important terms. So, for example, if we have this term here, A, I, B, I, this essentially just means that we sum over the indices which appear twice. And I have here some examples of this writing. So probably this way of writing tensor terms will appear later on. So go back here if you're not familiar. Okay, now we've written down the equations of motion before. This is now the slide already shown by Henrik. So what you introduce we can assume a two-dimensional flow. So then your Stokes equation of continuity we use this system. And then what Henrik was doing before was to introduce a decomposition into a mean value and a fluctuation value. We have this capital U plus U prime in the fluctuations value. So you do that for all the velocity components, you do it for the pressure, you also can do it for third direction if you want to consider three-dimensional. If we now consider U, V, and P, so the capital U, V, and P as being the mean values, the mean means an average in time, an average in example, average, or if you have homogeneous directions and average over space, then this decomposition into mean and fluctuation around mean is then called the Reynolds decomposition. The decomposition is actually. Now, the problem is when we consider transition, when we want to consider the linear development of disturbances in the boundary layer of the channel, then we were assuming linear, so that means small amplitude disturbances, in an effort to actually be able to throw away quadratic terms. However, now when we consider the full problem of turbulence, then we can no longer assume that we have small amplitude disturbances, so we cannot assume that their behavior is linear. But that also directly means we cannot just neglect quadratic terms. All these simplifications that we can do in the linear analysis shown before, we cannot do anymore. Essentially, what we have to do is we have to take the Reynolds decomposition, the decomposition of u into u plus u prime. We have to put it into our governing equations. We can then perform an average of these equations, and assuming that the average of the fluctuation is 0, and that certain cross products of fluctuations actually will vanish. And this is then the equation that we finally get. This is now the governing equation for the turbulent mean profile. We have here an equation for the evolution of the mean u here. We can, of course, in a similar way write down two terms now. We can also write down one equation for the mean. So now this equation we obtained, of course, starting from the Navier-Stokes equations, the general ones, by just introducing the Reynolds decomposition. Now, the important aspect, of course, as you will know, are that here are two new terms that appear, which have not appeared in the other equations. And of course, this is exactly what makes it a problem, or makes it difficult, or even impossible, to directly solve for a turbulent mean profile. Because these two terms here, the u prime and u prime b prime, are terms which are unclosed. So we don't have an equation for those equations, for those terms. So you cannot come up with a governing equation for these two terms. And these terms are okay, so this was all about turbulence in channels, so Reynolds decomposition, because this has nothing specifically to do with all bounded flows, but rather this would apply for any turbulent flow. But now let's move on to all bounded flows. So again, we have here these four canonical all bounded flows. We have the boundary layer, we have the channel flow, we have the tide flow, and we have the flow. Now for all of these flows, it's, at least for these three flows here, it is very obvious how to define how the outer length scale, so the size of the geometry is. For example, here it's the radius, and here it's the distance between the two plates. However, in the boundary layer, which is sort of the main topic of what we are considering here during this week, it's of course not so obvious. So we need to find some measure of how thick the boundary layer is. And then essentially we have here various definitions of how we can do that. I'm sure you've heard all about these various definitions. For example, you can have the 99% boundary layer thickness, which essentially is just the position at which the velocity profile has reached 99% of its freeze-through value. You can also look at displacement thickness. Essentially, that's sketched here what the physical physical interpretation of the displacement thickness is. So essentially, it would correspond to a profile that would always remain at u infinity and then abruptly go to 0, and would have the same mass flux. this would essentially then, that's why the name is called displacement thickness, this would correspond to sort of the size that the flow around far away from the body would feel as a sort of increased size or increased displacement caused by presence of this flow. So the definition here of the displacement thickness is shown there. You can also define the momentum loss thickness, which is essentially the same as the displacement thickness, just considering the momentum loss. Based on these two quantities, the delta star, displacement thickness, and theta, you can also define something which we call the shape factor, which is just the delta star. Now it turns out that for laminar velocity found there, the shape factor is 2.6, and when the flow becomes turbulent, this value is expressed in 1.3. But it's, of course, radius number dependent. The higher the radius number, the lower is the shape factor. As we will see probably later during this week, the shape factor is a very nice diagnostic quantity to sort of get a first impression of how a turbulent flow is actually looking. Okay. Now, let's first look at turbulent channel. Consider here this flow, we have two walls, one up here, one down here. We have the flow between these two walls, and we just apply a pressure curve. What we show here in this plot is just colors for colors of the streamlines velocity. Red corresponds to high velocity, and blue here close to the wall corresponds to low velocity. So instantaneously, one would have a velocity profile that looks something like this. So we have here, of course, at the two walls, we have a no-slip boundary condition, but then very quickly we will reach more or less a constant level here in the center of the channel, and then, of course, the same thing will happen in the upper. Now, again, this is an instantaneous profile. Now it's interesting to just see what happens when we look at this over time. So we just let the flow go. And we see, of course, that this instantaneous profile is fluctuating back and forth. But what we see also is that it always fluctuates, of course, within a certain range around. This, of course, is now exactly what the Reynolds decomposition is, the decomposition into a mean part and a fluctuating part is all about. So we can define now a long-time mean, which is in the solid line, and we can define here the fluctuation of the mean here by means of the square of RMS fluctuations around it. And you can see that the instantaneous values here, the blue ones, are sort of nicely captured by its decomposition into mean plus minus fluctuation. And of course, this is essentially a repetition. We have here the total quantity decomposed into mean fluctuation, and here we have one way to quantify the fluctuations by using the finite quantities. Of course, we can then also look at higher order moments of the fluctuations. So we can look at skewness profiles, we can look at flatness, we can look at PDFs and whatever. But of course, the important aspect here really is to see we need to decompose something into mean and its fluctuation. Okay. Now, let's be a bit more specific when we go to turbulent channel flow. So we consider really the most generic case of turbulent channel flow, which is given by this sketch here. So we assume that we drive the flow with constant pressure gradient. We assume a two-dimensional geometry. So that means that all derivatives in the span-wise direction, the span-wise direction is what we notify that Z is 0. We also assume that the mean value in the span-wise direction is 0. We assume that we have fully developed turbulence. So that means in terms of the mean values, there is no variation in x, no variation in time. The continuity equation directly gives us, because we have w equals 0, and the streamwise dependence is also 0, directly gives us the mean vertical velocity component is also 0. This is the result. Continue. Now, let's start now with the two-dimensional Reynolds average Stokes equations. So here written without any simplification, but if we put in everything that we have here into these equations, then we actually see that most of the terms luckily fall out. So the particular non-linearities here on the left-hand side will fall out. We have here the streamwise derivative being 0. These two terms fall out. B is 0. So this So there is obviously a chance that we can learn something from looking at these equations. The first step is to look at the y equation, so the whole normal momentum equation. That's first line here. So if we just write down, we see that there's only two terms left, this dp dy and this vd term. So we then see that for this term, the whole normal derivative is 0, and we can integrate that for this, and then we can see that we have a streamwise varying pressure gradient, or pressure, PW, which is then on this side. This is the result of the whole normal momentum equation. If we just collect all the terms that remain here in the streamwise momentum equation, it's just these terms and these terms here which remain. Now, we have learned something here about the pressure, the streamwise dependence of the pressure. So we see that the only term that the term that is actually dependent on x, this is PW. P and VB is not, if we put in P, or let's let it, VB is not streamwise dependent, it is PW. So we can replace this P dx with this dx. This gives us the combination of the streamwise and the momentum. Again, this is all without any approximation, apart from just assuming all these assumptions. So now, with this equation, we can actually use the idea is to integrate this equation in y. We integrate this equation in y, we can then use boundary conditions, which we have, which of course know at the wall. In particular, we know at the wall that there is no Reynolds shear stress. And the other aspect is we can define here at the wall shear stress, so the stress that is acting on the wall as using a integral force balance, we can relate this shear stress at the wall to actually the pressure gradient that is acting in the wall, essentially as if we consider this to be our channel, so this is straight, and we have here pressure forces, and here at the wall we have the forces coming from the shear stress, and this is essentially what is written here in this integral force. So by doing all this, so integrating the y using boundary conditions and using this this new term times w, we essentially get this equation, which is still without any additional assumptions. So we relate here the wall shear stress to the difference between the viscous stress and the turbulent stresses or the rate. This term here essentially comes from pressure, where we have viscosity. So, what can we do now with these equations? Or what do we learn about this? Now, the interesting, or the next aspect is to do something similar as we have done with the Stokes equation very much at the beginning. We like to find a new way of scaling these equations, namely in such a way that still all the terms remain present. So that we do not scale out the certain forms. Now, when we just look at the dimensions of all the terms that appear here, we can see that we have essentially two-dimensional groups, velocity and length. And based on that, we can define a velocity scale which is based on tau, so wall friction, and we can similarly define a length scale which is then defined on the wall friction. First, the velocity component is called the friction velocity, usually called tau, and the length scale usually is written as L star, which is the viscous velocity. If we now consider quantities that are scaled by means of u tau and L star, we can then introduce something that we call the inner scaling, or the wall scaling, or the viscous scaling, or simply just plus scaling, which essentially just means when we rescale, for example, u with u tau, this gives us u plus, or similarly u plus. At the same time, of course, we also have our outer length scales present. So that's, for example, the diameter of our pipe, or radius of our pipe, the distance between the two parallel planes, or, for example, the focus of antenna. But the important aspect here is that if we use these plus units, when we just put this scaling into this above equation, this is what we get. 1 minus y plus divided by h plus, here h plus is the channel height rescaled with star, is the u plus, or the y plus, minus ue plus. There are another two important aspects here. If we start now to define the Reynolds number based on plus units, essentially u tau times L star divided by nu, we will get as a Reynolds number, actually the Reynolds number is 1. So that means that on the level of u plus and y plus, we have highly viscous flow. If we define a Reynolds number based on, for example, the boundary layer thickness, or the distance between the plates, so based on the outer length scale, forming delta plus, then we get something that we usually call a tau, or the friction Reynolds number, which is a Reynolds number which somehow describes the intensity of the turbulence of those two. Now, it's of course very interesting to actually see how these terms from this momentum ballast actually compare to each other, how they depend on the distance from the wall. So I just wrote down here the four terms. So 1 equals du dy minus ub plus 1 plus h. Again, this term here corresponds to the viscous stresses, and this term corresponds to the turbulent stresses, and both of them together are the total stresses. Now, if you just look at this, at the contour, the magnitude of these terms in the turbulent channel flow, and we see here, let's assume that the wall is somewhere here. Of course, it's a box case of the wall far away here. So this is increasing wall distance. Actually, these various lines here correspond to different Reynolds numbers. So close to the wall, so when we are very, very close to the solid wall, then we see that the blue line here is essentially the dominant quantity. So that means close to the wall, it's of course viscosity being dominant. So the viscous stresses are most important. However, as soon as we reach maybe a level of 10 plus units from the wall, the viscous stresses drop drastically, and then further away are not there. In a similar way, the turbulent stresses, they are zero at the wall, of course, to the condition. They are zero, and then they go quickly, and then once we have reached the middle of the channel at the end of the line, so the important lesson here to learn is that close to the wall, it's of course the viscous stresses that are important, whereas further away from the wall, it's the turbulent stresses. Now, what does that help us? Actually, it helps us quite a lot. Namely, we can come up with sort of a description of the mean velocity profile in a turbulent wall flow. So, let's just look here at the typical velocity profile. We plot here u plus versus the wall distance y plus. Of course, close to the wall, at the wall we have the boundary condition, and then we, at some point, we reach the free stream. So this is a typical profile. I think it was maintained around 5,000–6,000. Now, the usual way to actually plot this is, of course, in this usual form where we plot the wall distance in the rhythmic form, where we then see this shape that we see. Deep region, rhythmic region, then we reach close to it. So, now our idea is to use what we've learned before, essentially that we have viscosity being dominant close to the wall and maybe less dominating further away from the wall. We want to use this to come up with a better or with a description of such a curve. Essentially, we want to distribute, or we want to cut it, this profile into various parts, and come up with different scalings for these various regions. Again, the important thing was in a region very close to the wall, we have learned that viscosity is important. Reynolds stresses are not as important. Essentially, we can just set these to 0, and since we're close to the wall, it's small. So what we get is 1 is u plus y plus, so we have constant slope, which gives us a linear velocity. U plus is 1 plus. So this is what we usually call the viscous cycle. Then the experiment or simulation show this is varied really up to the but it was the easy part. Now, we can also do something in a region further away from the wall. Namely, if you consider now a flow which is high Reynolds number, high Reynolds number essentially means that this delta plus that I introduced before is very low. So that essentially means that if we consider high Reynolds number flows, or high Reynolds number turbulent boundary layers, then we will have two different regions. An inner region in which the viscosity is still noticeable, and we have an outer region where viscosity should be, or the velocity profile should be independent of viscosity. So we can say that our velocity profile is dominated by two different shapes. One is this u inner, and the other one is u out. One of them independent of viscosity, and the other one is the effect of viscosity. Now, if we have a description here of these two velocity shapes, and essentially it means also at some point they need to overlap. at some point, this profile needs to be the same as this profile. That means that we should have an overlap region, which we then can, an overlap region in which both of these descriptions should be that. Now, in an effort to proceed further here, we can just continue here with this inner profile and just write it in non-dimensional form, so we can normalize it here with u tau, giving essentially u plus here as a function of the other dimensional parameters. In a similar way, we can do that for the outer, for velocity profile in the outer region. Here we write it as a deficit law of u infinity minus u. This is then a function of the wall distance normalized with boundary thickness. Essentially, this is the same as before, so we write u plus inner is f of y plus, and u plus infinity minus u plus outer is f of, is a function of the wall distance normalized with boundary thickness. Now, as I said before, there needs to be a region where these two profiles need to be, these two descriptions need to overlap, so they need to be the same in some sense. Now, the idea here is to actually look at the slope of these two functions. The small level f with the large scale, the large capital F. And the idea is that if we look at the slope, and the slope for these two functions has to be the same, irrespective of whether we look at the inner or the outer description. So this is what we do. So the inner over dy should be the same as the whole over the outer. This we can do. We can just go back to the description in terms of f, capital F. Just write it here with all the inner derivatives. Setting them equal. Then we can multiply with y. And then we see that if we multiply this with y, we actually get y plus. If we multiply this with y, we get this eta term. Now the idea is, or the important aspect here to realize is that the left-hand side is only a function of y plus, whereas the right-hand side is only a function of eta. So if we really want to make those sides to be equal, we have to realize that both of them have to be constants. Otherwise, because they do not depend on the same quantity, they will not be equal. So we can write the left-hand side equals the right-hand side equals a constant which for the moment we call c. Then we can reach for both regions, so f, small f prime here is c over y plus, and the capital F prime is minus c over a. Both of them independent regions. We can integrate both, so we get c times logarithm of y plus b, here similar. But this is now the famous result that is first derived, I think, in the 30s, which we call nowadays the logarithmic function. Essentially, it means that if we now look at the coming from the inner region, we have here u plus is 1 over k, which is this constant that we had before, times ln of y plus b. And if we come from the outer region, we have the velocity deficit law, which essentially is also having this logarithmic dependence. Now, as I said, the constant c is now, we just renamed this to 1 over k, and 1 over kappa, and this kappa is what we call the Karman constant. When you do simulations or experiments, it turns out that these descriptions are valid for a region of approximately between 30 or so viscous units from the wool up to maybe 0.3 times. So over a fairly extended region, we have something that resembles a profile. Now, the constants that appear here, in particular the kappa and the V, they might not be as constant, or there might not be so much agreement on what these constants really should be. It turns out for low Reynolds number flows, a good approximation is maybe for kappa 0.41 and for V 0.2. This is the values that are recommended by Hope here. Again, there is of course no theoretical justification for these values. This is just fitting the data. Westerlund, by looking at his high Reynolds number data, they suggested kappa 0.38 and the V, which is somewhat lower, 4.1. Then of course there are also other geometries, pi flow, for example, the very high Reynolds numbers, there we get kappa 0.43. So there is a certain spread for these parameters. But still, I think the important point here is less what exact parameters one should use and one can use, but rather that by just essentially doing fairly simple analysis of the common equations, we can come up with a very specific result, which seems to be a good prediction or an approximation to what we actually get in a very complicated problem. So in the end, we can come up now with a complete description of the velocity profile in a boundary layer. Very close to the wall, the green region here is the viscous sublayer, which we have derived our linear velocity profile. We have here the light blue region, which corresponds to the logarithmic region or the overlap region. Connecting the two is buffer region, and above the overlap region we have something called the wake region. And in the turbulent boundary layer, of course, at some point we sort of leave the boundary layer, and then we are in a region where essentially we have constant velocity, which is then essentially by potential. And here is just one slide to show how good or this approximation is. We have here a plot from Hassan Wahid. It covers a wide range of Reynolds numbers measured in wind tunnel. One can see that essentially irrespective of the Reynolds number, we always have here a good part of the boundary layer following the logarithmic region. So this 1 over kappa times 1 over cos. Also here in the velocity deficit law, so when you come from the outer from the outside, also here you have a very good overlap of these curves. Now based on all this, we can come up with sort of a map showing what parts of the boundary layer belong to what regions, up to where the viscous sublayer goes, where the outer layer starts, what is a function of Reynolds number. This is a very nice plot which you can find in the book by Pope. I don't want to go into details now, but essentially just sort of gives you an idea of how far the various regions go. And the last point that I'd like to make about this law of Moore, the logarithmic region, I mentioned it before, the universality or the non-universality of Karman constant, kappa, and B. Essentially, it's really not clear what this value should be. It's not even clear whether all the canonical flows we should actually expect to have a uniform, one single value for kappa. So there is a significant spread between various pressure gradients, channels, and pipes. But again, I think the important part is not really the values, but rather the shape. So I think before we continue now with fluctuations, I think we have a little break and we can continue with in 5-10 minutes. Everything here is scaled custom. First of all, you see that also that at the boundary layer edge of delta 99, we still have outside a little bit of fluctuation. Essentially, that means that instantaneously we will have turbulent motion sort of reaching outside the boundary layer edge. So the boundary layer edge is not really like a hard limit to turbulent fluctuations. Then when you go close to the wall, you see that a particular URS, so the fluctuations in streamlines direction, has a very, very large. It's much larger than all the other fluctuating quantities. So of course indicates directly that turbulence varies by no means isotropic, but rather it prefers a certain direction. Of course, this is just the picture of the turbulent streaks that we're going to look at. But in principle, this picture here shows sort of the qualitative behavior of the various fluctuations inside the boundary layer and also here the cross spaces. Actually, it will turn out that when we increase the Reynolds number, that the maximum value here of the UV cross stresses will more and more approximate the value of 1. Now, so this was the fluctuation. Now the next thing is, okay, is there, when we talk about fluctuating field, is there some sort of, what ways does the energy go in such a turbulent flow? So what we want to look at is now the budget of turbulent fluctuations. This is a sort of a picture of how energy is redistributing itself in a turbulent flow. So let me just explain to you what this plot means. So first of all, we have these blue circles. This blue circle corresponds to the mean flow. So the field, the velocity field composed of the average velocity. And this one here is the fluctuating field, sort of the circle corresponding to turbulence. And then down here we have something that we call the temperature field. For our consideration in incompressible flow, this essentially just counts to losses. So energy is flowing there and never to be seen again. So we have these three blue circles. We have here a green arrow, which essentially means that we need to put energy into the flow. We need to somehow drive the turbulent. Usually, this driving of the flow is a large scale phenomenon or a large scale force. So for example, in the turbulent channel flow, this would correspond to the pressure plate. Essentially, what we do is with this, we drive the mean flow. Say we put in 100% energy. Now, if we do all the equations corresponding to the kinetic energy of the mean flow, we will see that there is a term, which we call turbulence production, which will take energy from the mean flow and puts it into the fluctuating. So the mean flow uses energy to the fluctuating field. The fluctuations are actually driven by the mean flow, via the turbulence production. There is, however, also another aspect, which is the direct dissipation of the mean flow. So directly the mean flow, with the gradients in the mean flow, they will lead to dissipation between losses and production. So the energy we put into the mean flow is to some extent going into the fluctuating field and to some extent going into the temperature. And if you look at it in simulations, if you just measure how big these two parts are, it's about 50-50. For a low Reynolds number, channel flow, about 40% goes into fluctuations and 60%. Now, inside the fluctuations, of course, all the energy that goes into the fluctuations eventually has to leave the fluctuations and consume it in steady state. So those have to be at least 40% needs to go out here and before the turbulence. However, inside the fluctuating field, we have an extensive redistribution of the energy in terms of the components. So the energy mainly goes into the U component and is then redistributed into the other velocity components. We have viscous transport and we have turbulent transport. And it's exactly this part or this circle that we want to look at a little bit more detail now for a flow close to turbulent flow close to a wall. Essentially, we have here written down all the various terms that are responsible for the energy transfer in near turbulence. As I said, one important term here is the production term. That's where the energy comes from the mean, ultimately from the large scale force. This is, of course, a term which is usually a gain term, and we gain energy for the turbine kinetic energy, and it reaches here a level of magnitude of around 0.25 in this plus 16. The negative term, the one that takes away energy from this fluctuation, of course, the turbine dissipation, which peaks here close to the wall. These are the only two terms that actually correspond to a net energy transfer, so that they are, if you integrate them in the wall-normal direction, they're actually not zero. But we have here a number of other transport terms, so they only transport energy from various positions in the flow to another position. They don't really destroy or produce energy. We have viscous diffusion term, which is has maximum gain at the wall, then it has a negative loss or a little bit further away from the wall. Essentially, this term is redistributing energy from this region towards the wall. We have the turbulent diffusion term, also this one, sort of redistributing energy. And we have the pressure transport. Pressure transport term in the budget for the turbulent kinetic energy is not so important, however, for the budgets of the individual radial stresses or fluctuations, it's very important because this is the term that actually provides the distribution or redistribution of the energy between the various directions of those. So this picture here is fairly universal. It holds for channel flows, it holds for boundary layer flows, and it's fairly independent of the Reynolds. So the next slide here essentially just gives you the names and the formulas and the expressions for these terms. Again, the important part is that only the production term and the term of dissipation terms are terms that actually cause the change of energy. All the other terms are transport terms. One term I have not mentioned yet, which is the convection term. The convection term is zero in parallel flows. However, it's non-zero in spatially evolving terms. And even in boundary layer flows, which are spatially evolving, usually the magnitude at least close to the wall is values. Okay, now one little exercise here on the next two slides. I think I will not go through it, but I just encourage you to look at it. It's a nice little exercise to essentially predict to predict this point here, the maximum of the production. And by just doing these various steps, one can see that the production maximum in cost units will be 1/4, so 0.25, which I think is very nicely here reproduced by our simulations. And also we can see that the maximum, the position of this maximum will be located at y plus 5 to the power 12. I think it's a nice little exercise to really again start with very general approximations or very general equations, boiling down to a very, very specific result, as for example this. Okay. Now, excuse me for sort of mixing a little bit different things here. I have never really talked about how we, in boundary layers, how we essentially measure Reynolds numbers. I have mentioned it a few times, very tau, and I have mentioned very theta. And this slide is sort of just that it's formally introduced, so that as a reference. The various ways of defining Reynolds numbers. Essentially what we mean with the Reynolds number is either you can say how turbulent the flow is. The higher the Reynolds number, the lower the viscosity, the more turbulent, locally speaking. Or we can also mean with it how downstream, how far away from the edge, for example, or how thick the boundary is. And the various Reynolds numbers that we have used, for example, here's the friction Reynolds number, the rate tau, which is defined as given here. So essentially this is mostly used for channel flows, outflows. We have here the Reynolds number based on the momentum thickness. Remember again, the momentum thickness was related to, or similar as the displacement thickness. And this is a measure that gives an indication of how thick the momentum thickness is in the boundary layer. And obviously this is used mainly for boundary layers. We have here the Reynolds number based on the streamline distance. This was already used in the lecture by Hendrik as the streamline distance from the leading edge here. So x is the distance from the leading edge. And mainly for channel flows or pipe flows, we can also define Reynolds numbers based on, let's say, the bulk velocities, the integral velocity. So these are various Reynolds numbers. They all sort of indicate how turbulent the flow is, but they are used for different flows with slightly different. So why I wanted to show you now this Reynolds number essentially is because it's also interesting to see what kind of Reynolds number ranges do we actually talk about. Now, this is a slide taken from the thesis by Jens Österlund. Essentially, here we have a theta, so the Reynolds number based on the momentum thickness, and we have various experiments or scales for indicating sense. So the largest scales, of course, are planetary scales or atmospheric turbulence, which are here maybe in the order of 10 to the 6. In terms of simulations, we reach here maybe 10 to the 3, so 1,000 to 2,000 in terms of the theta. Wind tunnels span the region from a few hundred to 10,000s. And technical applications of cars or airplanes also spans the region starting maybe at a few thousand. The important thing here to see is that what we can do with simulations at the moment has not yet reached any technically relevant Reynolds numbers. However, with wind tunnel experiments, we somehow are scratching on the edges of this technique. Again, this is a very nice exercise to do, to derive, again, starting from the boundary layer approximations, coming up with a very simple equation, the Karman integral equation, which essentially relates skin friction to the growth of the boundary layer. But again, I will not want to go into more details here. If you're interested, you can try to look at this. Because now I would like to use the rest of my time, so the last half an hour, to talk a little bit about the structures of wool boundary turbulence. So far, we have only talked about scalings of mean velocity, scalings of fluctuations, so very abstract things. Of course, very, very important if we design an aircraft or we want to measure the drag of the body, but it's maybe not what is most interesting when looking at the turbulent flow. So, if you just look at simulations of high Reynolds number turbulent flows here in what you achieve as isotropic turbulence, so I'm sure you have seen such pictures. You get areas of high vorticity or areas with a lot of vortical structures, which essentially look like worms going through the domain. Now, this is a simulation that was performed at very high Reynolds number. However, it was performed in a domain without boundaries, because everything with periodic boundary conditions. Now, of course, the problem with turbulent boundary layers is that we have a boundary. Now, the interesting question is, how does the presence of the boundary, the presence of boundary conditions, influence the appearance of such a structure? Now, there has been a very nice review article in 1951, the annual review of fluid mechanics, and the author, Stephen Robinson, he essentially has a list here of a phenomenological list of structures, or how should I say, coherent structures which he could identify in a turbulent boundary. So he could see low speed streams, he could see ejections, he could see sweeps, and yet he could see coherent vortical structures of various shapes. You could see internal shear layers, pockets, you could see backs, you could see outer layer motion, you could see valleys, bulges, and high degree of intermittency, in particular in the outer region of the boundary. So there's a whole slew of different structures, different phenomena, different sort of interactions present in the turbulent boundary layer. So it's not at all simple to sort of just categorize it. But what I try to do now is to focus on a few of them and sort of show you how these actually look like in simulations and experiments. Maybe now you might wonder why I have here this picture of an astronaut, because this really has nothing to do with turbulent wool boundary flows. The interesting bit is that this S.K. Robinson is actually this person. So, I don't know, it's interesting that even when one does sort of this turbulent wool boundary flows, what we get something.
He's the astronaut.
So let's start now with probably the most dominant structure here, the low speed streams. Now, I have it already on the list of the landmarks of turbulence in the beginning of the talk. This is an experiment performed in the 60s in US. And this is an instantaneous view from the top of the region close to the water. Flow is going from the top to the bottom, and I guess they have released some bubbles in the boundary layer, which then sort of follow the coherent motion in the whole region. And what one sees here is that the boundary layer close to the wall, or the near wall ridge, is by no means uniform. There is some clear, streaky pattern. So there is some structures there which appear to be very elongated. And it turns out that these are really, it's like one of the fundamental building blocks of near-wall turbulence, these so-called turbulent streams. And it turns out that they actually have a spacing which is fairly universal between various wall-bounded flows, channel flows, boundary layer flows, pound flows. And the spacing is on the order of 100 to 120 plus units. Now, of course, the question how, of course, one way to identify these structures is by just plotting them instantaneously, but there is, of course, also a more systematic way, a more statistical way of extracting these near-wall structures. And one way to look at them is by computing span-wise two-point correlations in a plane very close to the wall, let's say 10 plus units away from the wall. I think this picture here is not taken 10 plus units from the wall. Essentially what one does is one computes this quantity and averages it over time. Essentially it's the span-wise two-point correlation of streamwise velocity. So we correlate u at a certain span-wise position with itself at a slightly moved position. Then one plots it, the result as a function of this displacement. What one gets is then plot something like that. Of course, if we start at a displacement of 0, and if we normalize it with the respective RMS value, then of course we have perfect correlation, so we get a correlation value of 1. And then we see that correlation gradually decreases, reaches a minimum at some point, and then goes up and reaches essentially a value of 0, which means it's uncorrelated. Now it turns out that this minimum here, for example, for this for the span-wise two-point correlation streamwise velocity component, this negative minimum, or the first minimum, would correspond exactly to that displacement where we have a high-speed streak and a low-speed streak. Because then the velocity difference is somewhat the largest and the correlation is the most negative. So the first minimum would correspond to actually not the spacing of, it corresponds to the spacing between low and high-speed streak, and the streak spacing, so the spacing between two high-speed or two low-speed streaks, would then correspond to double this value. So from a plot like this, which we can calculate from a turbulence simulation or from an experiment, we can directly deduce, okay, we have a minimum at maybe 50, 60, so the streak spacing will be 100 plus. This is a nice way of computing the coherent structures close to. Now, of course, there's a lot of theories about what these near-wall or these turbulent streams actually are. One can consider them to be part of quasi streamwise vortices, which essentially lift up fluid and push down fluid, and sort of creating then the deficit or the high-speed and low-speed streaks. One can then also think of having these quasi-streamwise vortices having some additional flow structures corresponding, for example, here to a hairpin vortex. This is something that we have. So there's a lot of sort of vortex dynamics or additional aspects that we can then connect with coherent structures close to it. At this point, I think I will not go into more details. Because there's other things that are important that are also present in the list provided by Robinson. And essentially, that's something related to injections and sweep reactions, which are also something very dominant when it goes to the wood. Essentially, this plot shows what is meant here. So consider when you put a little bit of dye into the near wall region, you will then see in an experiment that this dye will usually stay for a certain while very close to the wall until it is lifted and sort of violently bursts away. This is what we usually call injection. And one way to quantify how these injection motions, or also the sweep motion, which corresponds to the opposite behavior, can be quantified, is shown here in the so-called quadrant analysis, where you just plot all the events in a diagram, U versus V. Now, if you go back thinking about the production term, it turned out production is proportional to minus UV times dY. So it is the quadrant 2 and the quadrant 4, which actually produce turbulent kinetic energy, which here is giving a positive production in the turbulence function. So the ejection motion is exactly what I described here. So it's violent outburst of turbulent flow. Essentially, this means that we have negative U, disturbance U, and a positive V. That means that in a low speed stream we have fluid going up, ejection, and so the opposite, where we have positive U and negative V, which is speed fluid goes closely to. This is what we call sweep. So this is also something that is relevant in real world turbulence. Another aspect which has particularly recently gained a lot of interest is to look at large-scale motion, which is also very dominant in real world turbulence. So here you see a sketch from the experiment in 2077, 2 years ago, the side view of a boundary layer. What is plotted here with this wiggly line is the edge of the boundary layer. And what we can see here is that, first of all, that this edge of the boundary layer is not at all smooth, but rather it's very corrugated, and it's dominated by very deep valleys into the near wall region. And by now, so looking at such pictures, and we can come up with measures, angles of these valleys, we can come up with approximate scalings, length or heights of these structures. But the important thing here to realize is that the boundary layer edge of the separation between the rotational fluid flowing away from the wall and the fluid close to the wall, which is rotational, has vorticity, is not at all smooth, but really very, very hard. Now, pictures like this are, of course, very, very, very nice to look at, and they're very instructive, but they don't really give too much quantitative information. It's very similar to the streaks picture that we saw from Klein before, which of course are very, very instructive, but they don't really give you a statistical quantification. One way to also quantify these large-scale motions is, of course, again to look at statistical quantities, and in that case, this would correspond to computing spectra. Spectra, for example, spanwise spectra, streamwise loss. So I just want to show you here on the next 2 slides how one relates spectra to two-point correlations, the two-point correlations that we have seen before, and then also show you some results for such spectra. So again, we can start with spanwise two-point correlation, and the idea there is one measures the correlation or the autocorrelation of the signal sort of slightly displays. If one performs a Fourier transform of a two-point correlation or an autocorrelation, what one gets is a power spectrum. If one normalizes it. So the relation between two-point correlation and the power spectrum is Fourier transform. So, yeah, that's essentially everything I wanted to say here. Now, another aspect is, usually if one plots a spectrum, the usual way is to plot it in log. And you have, for example, in turbulence, then you have the k to the minus 5/3, which is then obviously a straight line. This, of course, one can also do here. I just want to mention here one important aspect here. If one wants to compare energy at various scales, and one plots an axis in logarithmic scale, then of course one cannot directly compare the area below the curve, because the x-axis is its scale. However, if one uses the so-called three-multiplier spectrum, if one multiplies this phi here with a wave number, then we can see here that we can still, even if the x-axis is plotted in logarithmic scale, we can still compare the areas below the curve and get a direct comparison between the energies contained in various scales. This is the reason why such spectra or boundary layer flows are usually plotted as three-multiplier spectra. So I just like to illustrate this process of going from two-point correlations to spectra during this series of slides. So we start again with the two-point correlation of the streamline velocity component close to the wave. Now we consider a high-variable boundary layer flow. We have here first minimum, which corresponds to the street spaces. So this will be on the order of 50, 60 plus units separation. We also have here a deeper dip, which corresponds to exactly these larger scale motions that I mentioned before. But this will be seen later on. So the first thing is we perform an FFT of this. So we go here from R into phi. The FFT there. And of course that means that the x-axis goes from the spanwise spacing into the spanwise wave. And then the usual way, as I mentioned before, is just to plot it in log, and you get something that looks like this. And hopefully it goes down here, so that means that actually the original simulation data was reasonably decent. But now we can do what I said, that I mentioned before. Or we can go here for the x-axis. We can go from the space of k, the wave number. We can go to the space of scaling of length, which is probably a little bit more natural for us to talk about a certain spacing, 100 plus unit spacing.
Where the minimum peak is, the autocorrelation is still positive. So that means just fast and less fast, it's not opposite direction.
Yes.
So that's also considered less.
Well, it's just position of where they are most different.
Yeah.
But then, of course, the problem is that we have here the largest motion, which is sort of the focus. If you go to lower Reynolds numbers, then this one is so anyway, so going from here to here, the only thing that I changed was essentially using here the wavelength in terms of the wave number. Now, next aspect here is to actually use here a box scale, and then we want to be able to directly compare the various energy contents below curves. We need to use here the pre-multiplied spectrum. This is what I showed here for the same data that we originally started with up here. It's exactly the same data, it's just Fourier transformed and pre-multiplied. Now actually we see a lot more which was before hidden in here. So first of all, we see of course this peak here, the first peak which is located at this 100, 120 plus. This corresponds to the streaks next to the wall. But then we also see here slowly an emerging second peak, which is for this particular Reynolds number located a little bit above 1000. Will turn out later that this corresponds to approximately 0.8 times the boundary thickness. So essentially what you get here is that the two-point correlation has the information of peak here, which scales in inner limits, which is the spacing of the streets, but also second peak, which was much wider, which corresponds to larger much. Now, this was at one y position, so y plus being 7 o'clock, so very, very close to it. But we can essentially do the same plot here for various heights throughout the boundary layer, and then we can get such colorful plots here. So you have to imagine the previous plot was just sort of one cut from here along the specific y position. So what we see here is span-wise pre-multiplied spectra at increasing Reynolds numbers. So here we start at a peak of 1000, 2000, 3000, and 4000. And the important aspects here are that we can see that actually the increase of Reynolds number really starts to change the spectrum. The important part close to the wall, the dominant structure close to the wall, of course, is, as I said now many, many times, are the near-wall streaks with the spacing of around 100. They always stay more or less at the same positions irrespective of the Reynolds. However, this peak out here, with the spectral peak further away from the wall, that moves according to the Reynolds number. And it turns out that span-wise distance or span-wise spacing of this outer peak is very, very well correlated to the boundary layer thickness. That's exactly this 0.8. So we can use spectra or two-point correlations so prepared in a nice way to really get a quantification of the sizes that are of the various structures that are present in the boundary. Okay, now that we introduce these spectra, let's take one step back and just look at some flows, look at some turbulent boundary layers. We've already seen the top view, the one from Klein and co-workers, and the streets. Now we look at sort of wall normal planes through the boundary layer. Here we have one picture from Jimmy Wallace, here from Hassan and Keeb. I don't know what the Reynolds numbers were for these pictures, but it's probably a few thousand. And of course, what we see here is essentially the same as we had in the sketch by a few slides before. We have here the edge of the boundary layer, then we have these deep valleys where we have free stream or the rotational fluid reaching levels very close to the wall. Again, we have the corrugated boundary layer edge with large vortices further away from the wall, but we also have very, very tiny vortices here close to the wall, which we can see. Now, one interesting aspect is now to see whether we can also find similar structures in numerical simulation and how numerical simulations of high-range number of parameters actually relate to experiments. This is what I want to show next. We have here a visualization of a flat plate. That's not yet too exciting here. Essentially, the flow is supposed to come from from down here going up there. We're looking at a section of ray theta being approximately 4,000. If we just put a cross section here on the side with just colors proportional to velocity, with red being free stream velocity, and over you can see it is bluish, very close to the wall. This will come to this. Cross stream plane here. Already here you see that we have these deep values in the boundary layer. Let's put a bit closer. Now we can also put a velocity plane close to the wood. Now essentially we see all these structures that we talked about. Heavier streams is alternating blue, yellowish structures. And here comparison to the experimental picture. And if we compare here the side view, of course also that is very nice to use numerical simulation. Now, based on the spectra and just looking at this flow, we can also come up with sort of a qualitative sizes of these various structures. For example, we can see here the spacing between streets is this magical number 100 plus units. The length of maybe one identifiable individual street might be in the order of 1,000 plus units long. But we have these larger scale structures here, which you see at the wall, which are in the order of 1, 2, 3, 4, delta 99 long. Here on the side, the same picture. Of course, the boundary layer thickness is here delta 99. The length of these individual packets is in the order of 50 delta 99. And in the spanwise direction, we see that these structures are essentially round or quadratic, having a height of approximately. In some sense, this is a view, at least for these lower Reynolds number turbulent flows. These Reynolds numbers that we can nowadays reach fully resolved simulations. Now, so this was just based on velocity. Of course, the next question is, can we look at actually how vertical structures in such a boundary layer look like? And this we can do in numerical simulations because we have the whole velocity field available, so we can just go in and visualize vortex cores. Here we have done it by means of the lambda-2 technique. So here we just visualize the vortices close to the wall. We can then also add some more vortices which are further away from the wall. And that's the last visualization here. We can just put in the boundary layer edge, so an isosurface of, I think it was 0.8 increase in velocity. So just to show you how corrugated, how wavy, how unregular the edge of the boundary layer is. Okay, now the last series of visualizations, again just more in a qualitative effort to show you how our boundary layer is looking like. I have here a few visualizations taken from a recent simulation that we performed on 7.5 billion grid points. So we just want to look at various places here in the flow to see whether the vertical structures, the vertical turbulent structures are dependent, or how they are dependent on the Reynolds number. So we can start here directly at close to the leading edge, This relates to what Henrik was saying before, that it's very difficult to understand transition even if one wants to study turbulent flow. Because whenever we have a station developing turbulent flow, we need to generate transition flow, we need to generate this turbulence in some way. And there are very different ways available in the literature, and it's not at all clear how efficient or how good they are, or how fast they actually lead to transition. We have chosen here a way which is very similar to experiments. We try to imitate the tripwire or a sandpaper, which is to generate transition here, and we calculate actually through the whole transition process. And of course, not really surprisingly, close to this region where we initiate transition, our flow domain is full of flow structures that correspond to transition. I think we've seen some of these structures also talked by Henrik in the K-type transition. We have these little hairpin vortices all over the place. I should mention here that the color scale is just the distance from the wall. So when you see this red head, this corresponds to a lifted head of the hair. So if we go now to a region which is still very close to an inlet, but in my opinion still very much dominated by transition to turbulence, we actually see many of these little hairpins. I don't know how good the quality now is for this picture, but it's really all over the place, or hairpin heads of hairpin vortices. So close to the inlet, close to where transition happens, hairpin vortices are presumably the dominant flow structure. Now we can also go a little bit further downstream. This is now grade theta 2,500. Grade theta 2,500. This, I would say, corresponds to approximately where we can reliably generate the turbulence in wind. I think we know it's difficult, but this is sort of a Reynolds number where we can really speak about turbulent flow. Now, of course, the dominant flow structures have changed, at least in this region that we visualize. We cannot see any longer the dominant hairpin vortices. It's more, to me, it resembles more the vortical structures that we have seen a few slides ago when we talked about the homogeneous isotropic turbulence. So we have worms of vortical structures crisscrossing to the map. And of course, in a very similar way, when we go to the highest Reynolds number in this particular simulation, it's 4,500. You see that the boundary layer has grown because we have the highest Reynolds number. But we also see that everything is dominated by large-scale structures, and the vertical structures are sort of like okay, now we're soon finished because it's soon 6 o'clock. I have now tried during the last few minutes just to show you some of the key aspects of these coherent structures. Of course, what I have not mentioned is that there are a lot of controversies and also some uncertainties related to all these things. For example, when I introduced the logarithmic law, I have not mentioned that there are alternative theories to the logarithmic law. So not even the scaling of the new velocities is beyond this discussion. Even more important is the scaling of the Reynolds stresses. That's also something which is unclear. Do the Reynolds stresses, for example, U or max, does it increase with higher Reynolds numbers? Does it saturate or something? Is there a second peak or not? They're all questions that are not really resolved. Then also here, when it comes to these inner and outer layer structures, to what extent do they interact? How can one quantify such an interaction? Sort of the summary here is we have a lot of data right now available, but there are still a lot of important questions open. And the ultimate goal is to understand turbulence in the sense that we can start to use predictive tools like turbulence models to actually help improving, let's say, this is a slide which is just listing a few references which might be useful for you when you want to compare or get some data with turbulent wall-bound flows. It's absolutely not complete. It's just the data that I have most recently used myself to compare data. So I don't want to go through this list. Essentially, we have here a list of simulation data and a list of experimental data. Maybe the most famous data are, of course, the cumulative user data, first list data, channel flow, and then the highest or most used channel flow data on Milenis, reaching up to the tower of 2003, and then simply look for. Okay, now we have 3 minutes left. Now we can go to the homework problem. It's a very nice problem which was suggested by Henrik. It's about estimating the dissipation for channel flow. And it turns out that we can make an estimate of dissipation by very basic means. Essentially, I don't want to go through all these steps here, but you can do it yourself and try to find out what this is all about. Yeah, so I would just leave it open as a discussion point, and Henrik will be happy to help everybody trying to attack this problem. Not yet finished. Summary. So there was a lot of things that I tried to show you. Many of the things we've certainly heard before, but it's always good to hear them over and over again. There are 4 points that are what we should take home. First of all, just to remind you of the Reynolds decomposition. We can then, for wall-bounded flows, we can introduce viscous scaling in terms of U tau and L star, which gives us the U plus and Y plus. Based on that, we can come up with the law of the wall, which essentially means that the parts of the velocity profile are more or less universal. So in 2 regions here, we have looked at the explicit formulas, so for the viscous sublayer and the overlap region. And then you can come up with the velocity profiles in this plot. And then the last part we also talk about the structures, flow structures in the turbulence, with the streaks with this magic number spacing of 1.5 plus units, but also these larger scale structures. Okay, so this is now everything. If there are immediate questions, then we can of course discuss them now, but since it's already discuss them tomorrow. Yes, this was it for today. Tomorrow we will again at 8:30.
Christoph, habt ihr schon gesprochen, wie es aussieht, was wir machen? Wir wollten irgendwie in die Altstadt gehen. Aber warum noch ein Total zurück oder direkt in die Altstadt?
Das weiß ich, also von mir aus gerne direkt, weil ich werde die Sachen da lassen.
Ja, das war eigentlich lustig.
Also, ich weiß aber nicht, wie es jetzt ist.
Da kannst du die Hausaufgaben machen.
Ständig.
Ja.
Nimmst du mit, damit er so machen kann.
Ja.
Oder du kannst mein Auto.
Dann würde ich wieder nehmen,